Good. Thank you very much, Sean. My name is Sifiso Ntshangase. I'm from the University of Zululand. Our university is actually located 2,000 kilometers away from iThemba Labs, Cape Town, where the previous speaker is from. So I'm going to talk about octupole excitation in uranium isotope, a measurement which we did at iThemba Labs in the previous year.
Sifiso, can you just run the presentation? I think it's not.
It's not appearing.
No,
full screen, Sifiso.
Okay. Slides. Okay. Is it
Thank
okay
you.
now? Okay.
Perfect.
So this. Let's remove this. So the project was actually inspired by the prediction of tetrahedral shape, and this shape is said to be characterized by by triaxial octupole deformation together with the non-zero quadrupole moment. Those of you who might not know, the tetrahedral shape is of this size, more or less like a pear shape. So if you do some Wood-Saxon single particle calculations, it shows some gaps which indicate the tetrahedral shapes for protons and neutrons. So these are calculations which indicate where this tetrahedral shape should be in, and the favored region. One of the favored region is in this germanium region, and the other region is in this gadolinium ytterbium region. But some studies at iThemba Labs has ruled out this, and the only remaining region to study tetrahedral nuclei is in the thorium uranium region. So that's, the biggest motivation why we opted to study in this region.
Sifiso, can you just move your camera a bit so that we can see your face?
Yeah, okay. You see me now.
Perfect. Thank you.
Okay. So the potential energy surface for double magic thorium, here you can see that the deformation is almost zero. The deformation parameter is almost zero here for quadrupole moment. And same thing for uranium, is almost zero here. So therefore, this means that there should be no in-band E2 transitions in the spectrum. Now let's look at the systematics in this nuclei where tetrahedral has been predicted. We start by looking at the radium isotopes, which has been studied before. And this band has been interpreted as the interleaf band. And this one, they have been interpreted as a split band. So none has been interpreted as a tetrahedral deformation. And in the thorium region, same thing, this band has been interpreted as interleaf band before, and this one is split band, and now they call this one octupole vibration, and later on this has been interpreted as static octupole or octupole phonon condensate. In the case of uranium, though it has been studied extensively, but they are missing E2s transitions. So one will ask a question: is this now the tetrahedral candidates? So we performed the measurement, You see, they are missing E2s. There's only these two tentative transitions which are in uranium-230, which were measured by Ackermans and Zane. The problem with the uranium-230 is that the fission is a major a channel. It's a dominant channel. So, but we use this reaction and the alpha XN reaction to populate uranium-230, and then alpha 4N to populate uranium-232. And of course, we use a very intense beam and a thin thorium target. This target was limited by the fact that we want the uranium recoils to pass through. So because of the intense fission background, so it was necessary to develop the recoil detector so that we suppress the fission background. So this is a schematic of our recoil detector developed at iThemba labs. It operates on a principle of the time-of-flight measurement. So it's the schematics like this. You have the beam, and you have the target. If it hit the target, and it produces some recoils, which then hit an aluminized mylar foil here, and there's a grid behind it, which then accelerate some electrons, because when it hits this, it liberates some electrons, and they are bent by the perpendicular magnetic field into a microchannel plate here where they are detected. So this is how our recoil detector works. So the time of flight measurement is measured with respect to the SSC beam pulse, relative to the SSC beam pulse. So it is of 340 nanosecond long, which give us a good allowance to measure as low as 270 keV recoils. Remember, the recoils for uranium-231, they were about 1.1 MeV, and the recoils for 232, they were about 700 keV. So you could able to detect them. So this is the setup, Aphrodite array at iThemba labs. This is the recoil detector inside here. So we made a foil here to allow the beam through without producing unnecessary background. So basically, this is located inside here. So now, these are the results what we get, because we get when you do gamma without the recoil detector, you don't see the uranium evaporation residue. But then when you switch on the recoil detector, you see the uranium lines. They are very much visible. So this was a good indication that our recoil detector is working perfect. So this is the same thing for uranium-230. So if without the recoil detector, there are no lines here. There are no uranium lines visible. But if you switch on the recoil detector, then you see the uranium lines. And you can also see the 511 being dramatically reduced. So we then sorted the matrix into, we then sorted data into the matrix. For the uranium-232, we get 7 million events, and for the uranium-230, we get 1.8 million events. And if you sum the gates into the ground state, you can clearly see the ground state band here, and the E1s here. The same for uranium-230. If you sum the ground state band, you see the clear the ground state band transitions. They are lying here, and so we have able to to extend the ground state band with 3 transition. But most importantly, we observed the E2 transition for the first time here. I mean, you can see them here. This is for 230. I mean for 232, and for 230, there was not enough statistics. So, in addition to the transitions that were observed by Ackermann, we able to identify 2 more transitions on that. So, and then we then calculate the dipole moments for using the rotor model, and the values are listed in this table here, and for uranium-230, and we then average them to get the data point, which we then plotted in trying to understand the systematic in the region. We plotted the data for radium from the previous measurements, and the thorium and the uranium. It's interesting that our uranium-30 data, it agrees very well with the measurement that was done by Ackermann before. We also compared the staggering function with the data. Interesting enough is that there is an anti-correlation between the staggering and the dipole moment. At the region where Octupole is region, where the traditional Octupole region, the dipole moments are very high compared to the staggering function. But at the vibrational region, the staggering function, which is actually a measure of splitting between the bands, is very high compared to the dipole moment. We then also compared the data with the dipole moments with the calculation, the Wilson calculations, and they agreed very well, except that at the very heavy nuclei, the calculation overestimate the data. You see, it's going high here compared to the data, more especially in the radium and the thorium. And what we also notice is that it is the isotone, not the isotopes, that have got similar energies. And we also plotted the different bands, the different octupole and the ground state bands. And we observe that the octupole bands is populated very weaker, and it moves far away from the rust line. This might be the reason why it was difficult to observe the E2 transitions, because as you move on, the octupole bands move away from the rust line, especially for the uranium, for the heavy uranium. But what's most important here is that a study on radium-226 was done, which was done by Uranium. He identified the quadrupole moments and the octupole moments for radium-226. And we have compared the branching ratios for radium-226 to the ones for thorium and uranium. And from there, we then because the radium-226 was said to be octupole. So one can make a conclusion that because they have a lot of similarities, also the uranium-238 and 232, they are just a normal octupole. So we can also conclude that we have studied the uranium isotope using the recoil detector. The uranium level scheme, of course, has been extended, and we have compared the radium-22 bands, and they are identical to the branching ratio of uranium to 232 and 230. And since they are identical, one can conclude that the uranium-230 isotopes that we have studied are actually not tetrahedral, but are just normal octupole. I thank you, and these are my collaborators, from most of them from iThemba and the other universities.
Thank you, Sifiso. Okay, there's ample time for questions.
So, Sifiso,
yes.
So what is happening with the new measurements that you were supposed to run at the iThemba labs? What is the status of that?
Oh, yeah.
With the recoil detector.
Thanks, Nico. We have actually, before this measurement, we have actually run 2 measurements. The one was for uranium-231. That's the analysis for that is still in progress. But we also repeated this measurement because here there was very little statistics, the uranium-230. So this is being analyzed by one of my students, Mr. Nkalanga. There was a challenge in this one because remember we migrated from the old digital, the old acquisition system to the old analog system to the digital system. So it is taking time for the student to analyze this. There are a lot of problems in the data, so it's taking time to sort. So it's still sorting.
All right, thank you so much.
Yeah.